Um, yeah, if we're seeking partial derivatives of, so we've got an equation such as this, say we're interested in partial of z with respect to x, partial z with respect to y. What those things are here, well, that's not going to be, we're not going to be able to do it quite the way we talked about last time, because yeah, we don't have z equals a function of x and y. Finding those partials when it's that way, is fairly simple. You hold one constant and then the other. Use the basic techniques we talked about, but what if we don't have a situation where I can't solve for z here, and so we're not going to be able to figure out what it probably is not even, then that z is a function of x and y, maybe multiple functions of x and y, but beside the point. If I want to find this partial of z with respect to x and partial of z with respect to y, I can use the implicit differentiation technique as we've discussed previously several other times. So yeah, remember, so if I'm finding the partial of z with respect to x using the implicit, yeah, what I'm going to do is I'm going to basically do the partial, take the what we call it, the ddx of both sides, but in this case it's the partial with respect to x of, well, of both sides, but besides obviously not anything consequence there, but since I am doing the partial with respect to x, the good news is y is fixed, right? We do know that, so that still pertains. So the y value still is fixed here. And so when I do the partial of this term with respect to x, that's kind of like what we did with the when we had it z as a function of x and y. But so the y is still fixed here, so that's still just going to be the derivative of x is 1, so that's still going to be 1y or just y. This, on the other hand, is a different story because I don't know what z is in terms of x and y. So what I have to do, of course, here I know you're thinking product rule there, right? So yeah, when I do this partial with respect to x of that, it's 3z cubed, 3z squared. But since I don't know what z is in terms of x and y, what I can do there, remember, is put the partial z with respect to x. When we were first doing implicit differentiation, it was the dy over dx. Well, in this case, it's the partial of z with respect to x is the term that I would put there. And it's kind of the chain rule because I don't know how, what to do with as far as that goes, but so all of that is what comes out of z cubed derivative with me there. But like I said, there's a product rule, so I have to then do z cubed times this derivative, partial respect. Well, it's an x, so it's just 1. Is that all right? All of this comes out of that one term. Now the last term there, in this part of it, I don't have product rule because, like we said, the y is fixed, so it's basically just like the 2, right? And so what would be the derivative we would put for that one? Do the partial with respect to x, so it'd just be minus 2y times whatever that is for for z, right? The derivative there is z, which again, by power rule, whatever, it's just 1, but since I'm doing the partial with respect to x, I also need that partial z, partial with respect to x term. Is that all right? That equals 0. And now, just like before, since what I'm trying to find is this, the partial of z with respect to x, we've got two terms that have partial z with respect to x, so I'll move the other terms to the other side, so subtract y, subtract z cubed, which gets rid of those two terms there. Leaves me, this and this, which I can then factor off the partial of z with respect to x. Z squared x minus 2y, so what's left? Factoring those off. And then divide off. Okay. All right, then. Okay. Same. Let's go ahead and do the partial y, z with respect to y, just to say we did one, I guess. But so that flips it around, right? So now the x is fixed, and we're doing things with respect to y. So yeah, so when I do the derivative with respect to y of that, that would be just x. This, okay, so what about that term? Maybe I should just rewrite it over here. So this is so what about that term? What's the doing the basically partial with respect to y now? Both sides. So this side's 0. So what's the partial with respect to y of that? Well, x is fixed, so really I just have to do the derivative there of the z, which is z squared partial z with respect to y, right? Is that okay? And then, last but not least, that one, well, that's going to be product rule because I've got y and z, so the derivative of minus 2, y would be minus 2, leave the z alone, and then the minus 2y times the derivative partial with respect to y there, so that would be just partial z with respect to y, equals 0. So it sort of looks like the other one, but a little different. All right, so move these terms over, subtract x, add 2z, through those, these two, so factor that off, 3xz squared minus 2y equals minus x plus 2z, divide that off, so same old drill. All right. Just the only drawback is to do derivatives, I guess you might say, in this circumstance. There's just two of them, and so it complicates things a little bit. But. All right. Now on again interpreting what we're finding here. All right, let's say we've got for z equals x squared plus y squared. Let's find partial of f with respect to x at 1, 2, and then interpret that, graphically speaking, what that means. Well, finding these is fairly, hopefully, really simple. The partial of f with respect to x would be, we're just keeping x's, what we're doing the derivative with respect to. So the y is fixed, so this is just 2x, right? And so f of x at 1, 2, partial of f with respect to x at 1, 2, well, that's just giving me the x is 1. And so I just plug in x to be 1. Sometimes you might need the y if y is involved, but here y is not even involved, so just plug in the x to be 1. So, no hard really thing there. But then interpret it on the graph. Okay, so I think we've graphed this one before, but let's talk about it again. Again, if you think yeah, we did graph this before, but if you think through it, again, we did this one because if you pick z to be like squares, like z is 1, that's going to give you x squared plus y squared equals 1. So as far as the level curve is concerned, at z equals 1, so at the height of 1, you got a circle centered at 0, 0, circle radius 1. And then at 4, z equals 4, the level curve would be a circle radius 2. And then at 9, it's out to a circle radius 3. Remember doing this one? Yeah, you get this parabola. And of course at 0, z equals 0, it's just a point, 0, 0, 0. So anyway, you get this paraboloid is what it's called. I should have widened it out. That's good. It just keeps going infinitely up there. Anyway, all right. So the deal was, let's interpret this here. Well, again, what we've done when you find the derivative with respect to x, the y is fixed, okay? And so what that means, what we're dealing with over here, since the y is fixed, and in this case it's fixed at 2, if you fix the y here at 2, which I'm trying to get it kind of accurate, so the y is fixed at 2, so if you think about the plane that y is 2 that slices through this paraboloid, get rid of these, got too many lines going here. If we think about this intersecting this, the y is fixed, so it's y equals 2. So we've got z equals x squared plus 2 squared, so that's z equals x squared plus 4. Well, you can see there that that's going to be a parabola itself, right? So this is going to intersect, what I'm talking about, the intersection is when the y is fixed at 2, it's a parabola, z squared equals 4, which, all right, so the vertex of that would be at x is 0, y is 4. I mean, x is 0, z is 4. Y is, of course, fixed at 2. Anyway, where's 4? It'd be right about here. So you get this paraboloid intersection. Hard to see it though. It's sliced at y equals 2, and so you get this parabola in the xz plane that's z equals x squared plus 4. And what this right here, so what does this provide right here? It's a slope. And it's the slope of that parabola at this, that would be 1, 2, and then the y, what's the x is 1, the y is 2, so that'd be 1, 4, so that'd be 5, right? 1, 2, 5. Of that parabola in the xz plane. So there's a lot going on. So 1, 2, and 5. See, that's vertex 0, 2, 4. So 1, 2, 5. It'd be up here. So somewhere like along around in here. That's what it comes out to be. So it's not just something that probably you'd automatically think, well, that's what that is, but it turns out that's what you got. All right. Now, if you have more than 2 variables, you can extend this. Like if I have a function of 3 variables, so if I have a function that's of x, y, and z, we can talk about partials with respect to x, partial with respect to y, and a partial with respect to z, and it's the same story. If I'm doing the partial with respect to x in that case, the y and the z are fixed. And so here, since y and z are fixed, this whole thing is just a constant. And so the derivative with respect to x would just be 1 times sine of y plus 3z. If I do the partial with respect to y, well, the x and z are fixed, so now I have to deal with the sine thing. So I have to do, it's kind of a inside-outside chain rule. The derivative of the outside would be cosine. Inside stays the same. But then I have to multiply by the derivative of the inside. Well, I'm doing the partial with respect to y, so that's 0 derivative. So the derivative of the inside is just 1, so that really doesn't bring anything else in there. And then, since it's a function of x, y, and z, I can also do partial with respect to z. Same deal, the y and the x are fixed. So that's basically the same story, except derivative of the inside, derivative of the outside is cosine, the inside stays the same. But the derivative of the inside, well, since I'm doing it with respect to z, I need to multiply by 3. So it's, yeah, we can extend it to 4 variables, 10 variables, whatever we want. Okay. All right, now,